So our last lesson was on Arrhenius acids, and if you haven't done so already, make sure that you go back and do the reading that was assigned on Classroom for Arrhenius Bases from the CK12 website. So that would be section 21.4 on Arrhenius Bases, and also do the little practice at the end. And I'll talk here in this video a little bit about some of the practice questions that are maybe a little bit tougher, or maybe you struggled with a bit. But first of all, an Arrhenius base, an Arrhenius acid, we talked about in the last lesson, is anything that increases the concentration of hydronium. So acid is anything that gives you more of this H3O plus ion. That was in the last video. Base is anything that gives you more of this OH minus ion. Now with an acid, if you recall, the way that an acid gives you more hydronium is that it actually reacts with the water molecule to turn it into a hydronium ion. So with an acid, and you don't have to write this down because we've already covered this, but with an acid like HCl, it actually gives its H plus ion to water and turns that water into hydronium and leaves behind the Cl minus. So that's what an acid does. And again, it's all about the fact that it's an acid, therefore it produces hydronium. Well, a base, let me get rid of all this stuff because we're talking about bases now. A base, according to Arrhenius, and this was just Svante Arrhenius, you read it in the CK12 reading, but basically prior to him, they defined things based on their properties. So if something tasted sour, it was acidic. A little dangerous to be tasting chemicals all the time to find that it's sour, but that's how they figured it out. They didn't have pH probes or anything like that. The same thing with bases. They tasted bitter, they were slippery, they knew some of the things that they reacted with, but they needed a molecular level definition, and so Arrhenius came up with one. Here's what's happening in an Arrhenius base. If I have something like sodium hydroxide, this is what is in Drano, drain cleaner. It's going to dissolve. So you see it says it dissolves in water. So if I have some solid sodium hydroxide, and that means just a Na plus ion, so sodium from the group number 1, the alkali metals on the periodic table, and then I've got an OH minus ion. So that's an ionic compound. And ionic compounds are soluble, which means they dissolve in water. Not all of them, but most of them. And so when we write an equation for that, what we do is, instead of saying it's reacting with water, the way that we did with the acid, is we put water over the arrow. And that just means that we're not necessarily changing the water molecule itself. We are just using the water molecule to split up the sodium the base, sodium hydroxide, into sodium and hydroxide. So in the end, I'm going to get aqueous, meaning dissolved, Na plus ions, and also aqueous hydroxide ions. And so if you can imagine a beaker with some water, bunch of water molecules floating around in this beaker. And technically, and we talked about this in our acid-base intro, there would actually be a little bit of hydroxide and a little bit of hydronium already in this water, even if it's pure water. But what we're doing by dropping the sodium hydroxide into this beaker of water, if I just kind of draw what a sodium hydroxide crystal would look like, or a little tiny piece of it. So let's say this little blue guy is sodium, and we'll make hydroxide red. So hydroxide is actually made up of O and H. So I'm going to draw like two atoms stuck together. So what I've drawn there is sodium hydroxide. And what happens is these water molecules surround the sodium hydroxide and get in between the positive sodium and the negative hydroxide and split them apart. And so what you end up with after a couple of minutes is this hydroxide is now off on its own. So we've created aqueous sodium hydroxide, and it's the presence of that negative, that OH minus. So I'm talking about this guy right here, that OH minus, that makes this a basic solution. It gives it a basic pH, It's what makes it effective as a drain cleaner in the case of sodium hydroxide. Is just NaO. I'm sorry, is just what they use in like Drano. And what we've just drawn is an ionization equation. So we talked last time about ionization of acids and how they produce hydronium. Well, this is the ionization of a base. It's simply dissolving. Okay. So in a base, you can always recognize, or usually recognize, it ends in OH. Okay. The other thing that the practice from the CK12 website kind of mentions and focuses on a little bit is distinguishing between these different metal hydroxides and which ones are basic, which ones are slightly basic, which ones are very basic. It all comes down to solubility. So it turns out that the metals in group 1, like if you were to look at the periodic table, in group 1 you would have hydrogen, which we're going to kind of skip that one, but the metals below hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Those are, and we're going to not have to worry too much about those guys at the bottom of the periodic table. Turns out that those group 1s are very soluble when they are with hydroxide. So if I have like sodium hydroxide, it dissolves very, very easily. So it turns out if we look at the group 2 metals, so like if I continue looking at the periodic table, next to lithium we have beryllium, next to sodium we have magnesium, and then calcium, and then strontium. Just kind of going down the periodic table, this is group 2. The group 2, and these guys all have a 2+ charge, whereas everything in group 1 is 1+. Okay, so if I look at group 2, those guys can form bases with hydroxide as well. They're just not quite as soluble. So for example, if I wanted to compare sodium hydroxide, which is very soluble, the one that we just did the ionization equation for, if I wanted to compare it to its next door neighbor there in group 2, magnesium, and I wanted to talk about magnesium hydroxide. Magnesium hydroxide acts just the same way that sodium hydroxide acts. It dissolves in water to form ions, right? And so those ions in this case would be Mg with a 2+ charge, right? Because magnesium is in group 2. And then instead of just forming one hydroxide, like sodium hydroxide just had one hydroxide in it, which is why I only have one hydroxide as a product appear. With magnesium hydroxide, you notice there's a 2 there. And that's because magnesium is +2 and hydroxide is -1. So you have to have 2 hydroxides. Well, that also means that when it dissolves, for every 1 magnesium ion you get, there's also going to be 2 hydroxides. So you're going to write coefficient 2 and then OH minus. And these should be written AQ for aqueous. And this over here is solid. So it's a very similar equation, but one of the things that in the CK12 practice questions that they bring up is the strength of these bases does depend on their solubility. And the +2 and +3 ions, like magnesium being +2, paired with hydroxide, actually holds on to that hydroxide a little bit better when you drop it into water. And so magnesium hydroxide doesn't tend to be quite as strong as sodium hydroxide because it doesn't dissolve quite as well. So you won't be able to get as many of the magnesium hydroxides to dissolve as you would the sodium hydroxide. So that's what that's kind of referring to. And then there's another question, and it sort of depends on, you may not have gotten this question, but it asks, which of the following are Arrhenius bases? And it gives you, or which is not an Arrhenius base or something like that. But it gives you like sodium hydroxide, which of course, has hydroxide in it. So it's an Arrhenius base. It gives you like, magnesium hydroxide. So same thing. Yes, that's an Arrhenius base. It's got hydroxide in it. It's going to dissolve to give us, a couple of hydroxides. And it gives you like CH3OH as a choice. Well, this is not a base, even though it ends in OH. And Can you think of, based on our examples and what we've talked about so far, why this one would not be a base even though it has an OH in it? So hopefully you said that, hopefully you said or thought about the fact that this is not a metal. And so if that's not a metal, CH3 is a couple of nonmetals. If it's a compound that's made up of all nonmetals, it's not ionic, which means when you go to dissolve it, it's not going to break up and give you hydroxide. So this guy would not be a base. And again, that question was in the online practice, and I just wanted to make sure, kind of clarify that that was the reason that that one is not considered a base. So an ionization equation for a base will always result in the formation of hydroxide. So there will be an additional reading assignment this week because I want to preview actually what we're going to talk about on Wednesday. And remember, we are doing Monday and Wednesday until further notice. One small lesson just like this one, along with reading to sort of preview the next lesson. So thanks a lot, guys, and have a good rest of the day.